All right, so this is where we left off, and this was a little bit of a tough one to maybe figure out in terms of your probability of success because it wasn't really totally clear. But this 2-to-1 ratio means that two of the candies will be strawberry centered and one of them won't be, which means there would be a total of three strawberry or three candies. So a 2 out of 3 chance that it's strawberry and a 1 out of 3 that it's the whatever the other one was, some kind of almond. Yeah, almond center. So this is your classical way to do it with your binomial expansion idea. But if I wanted to do it the new way in the calculator, uh, you both of these, notice, are an exactly equal to 4, and this was 2 of each type, which again meant in this case, if this is what I considered a success, was the strawberry cream one, then I'm interested in 2 strawberry creams, which means I automatically would have 2 of the almond ones as well. So both of these were in exactly equal to, so both of these would have been a binom CDF, not, oh, sorry, backwards, a binom PDF. PDF is when it's equal to. And so on the calculator, you could have done that again, just so you see where that is. It's in your second bars, and it is up here. PDF is equal to, and you could have put in those values right in there. The trials is your N. That is your actual probability of success, and X is your R value. So those are your answers, and if you did them with a calculator, I can tell you that you could have gotten, instead of a fraction down here, this one was 0.1975, 1975, great year, and this one would have been 0.2963, and there you go. And when you do probability, it's often a good idea to stop and take a second to make sure your answer makes sense in terms of what you're asking about. 2 of each type, one is way more likely to happen than the other, so it really wouldn't be that likely that you get 2 of each. You should get more of this one than the other one. And this is the reason this is getting all 4 of them the exact same type. Also not extremely likely because out of 4 candies, if this is a 2 out of 3 shot, there's a good chance I would have gotten at least one of the almond centers. So that's why both of these probabilities aren't extremely high. So I'm going to kind of just reinforce what we talked about on the first video in this example. It's not anything new, but I do want to again point out the difference between a PDF and the CDF and when you use it in your calculator. So, and this is was an example that was kind of already loaded up, but it's a little bit, I don't know, not super exciting to think about. But if in a hospital 60% of patients, so there's my P, that's a big number, 0.60, are dying of some disease, not COVID. We know that is not the COVID level of death rate, so that's good news. So this is some other disease, unknown, mysterious thing. So on a certain day, we have 8 patients. So if I have 8 patients being admitted, that's my fixed number of people being admitted for this particular thing. And I want to figure out these 3 different probabilities. One, that exactly 3 will survive. So that's going to be my X equals 3. And it's X equals 3, so it's a PDF when I do binomial. So that's your exactly. Less than 3 is right here. And that means I'm going to have to use the CDF if I want to use the binomial distribution in my calculator. But again, PDF is when it's equal, CDF is when it is less than or equal to, and that is important. It counts and includes a value as it tracks all the ones below it, and this less than 3 does not include 3, so I'm going to have to do a little fix here. And at least 3 means what is a probability that X is greater than or equal to 3. So depending on the whether it's less than, greater than, with the equal to or not equal to, dictates how you can use your CDF function on your calculator. So we'll talk about that more as we get into it. But I always start this by writing a little probability inequality or equality, depending, so I know what's going on in terms of PDF or CDF. It's just a kind of helpful little task. So this is an equal to. So if we're doing it the old school way, we've got 8 patients. So this would be 8 patients. And I want to know the probability that 3 of them survive. So I actually have to be careful now because I want 3 to survive. And in my particular calculation, 60% are dying. So this is not a success to me, obviously. So actually, if this is my probability of failure, so that's really my Q is 60%, and a probability of success is surviving. And so I have a 40% survival rate. So I have to kind of read it. They kind of twist that around on us. So that means I have 3 of these 8 patients surviving, so 0.4 cubed, and that means I have 5 of them that wouldn't, and so they pick up the other rate. And so you could do it the NCR way and do it like this, or if we go to our handy dandy calculator, I can, I'm in PDF, which is correct. I believe we had 8 patients. We wanted to know how many survived, so that's a 30%, what am I doing? 40% survival rate. And I wanted to know probably exactly 3 of them survive. So if I come in here and paste that in and hit enter, I get 0.2786 or 0.2787. So that answer would be 0.2787. So there is a 28% chance that exactly 3 of the 8 would survive. So now I'm to this with the less than 3. And again, when you can always build a little model. I'm not going to carry this all the way out to 8 because I'm only dealing with this bottom half of it. But, well, okay, I just did. So here are all my possible number of patients that could survive. And if I'm interested in less than 3 surviving, I am interested in this set of people surviving. Notice I'm drawing arrows to indicate that it's less than 3 is from 2 down. So really that means that I'm on the correct side to use a CDF because it's always less than or equal to, but it also helps me see that this is the same as the probability that X is less than or equal to 2. Because this is discrete and I can't have a half a patient, if I'm less than 3, it's exactly the same as being less than or equal to 2. And this I can do in my calculator with a PDF. Otherwise, you have to do 3 separate calculations like this, one for probability that X equals 2, one for probability that X equals 1, and one for probability that X equals 0, and add those 3 up. The calculator benefit here is I can go and do the cumulative one. So if I go to my calculator, and I go second bars, and I go to Binomial CDF. There we are. Again, we had 8 patients, and the probability of being well or surviving is 40%. And I will put a 2 in here, which just means it's because it's a CDF, it's going to calculate 2, 1, 0, and add all those up, paste it, and I get my answer of 0.3154. So this would be 0.3154. So about a 31% chance that less than 3 will survive. And then at least 3 will survive as X is greater than or equal to 3. And again, I can't do a greater than or a greater than or equal to in my calculator. So this is where I have to turn it around to 1 minus probability that X is less than or equal to, because that allows me a CDF. And if 3 is included in the values above, that's really all of this stuff, which means what's left over is what I already calculated. So if 3 is included in 3 or more, then the first number I would include in the less than or equal to is 2, and I already calculated that right here. So this answer would be 1 minus 0.3154. So I don't have to do a separate calculation because I conveniently already did it for you there. And so I can literally in my calculator go 1 minus second answer. I think that's answer. And we hit enter, and so it would be 0.6846. So that is going to equal 0.6846. So there you go. And that's how you kind of do those. Again, I can mess with you on changing the equal to underneath these inequalities or switch them around. You got to really think about it, but you can always also do your draw a model for yourself. All right, so here we go. You're going to pause this and you're going to try it. It should be very similar to the one we just did, except for that I don't think I messed with you. This one, instead of it being the opposite, I have a 6% defective rate, and I'm interested in being defective. So oddly enough, a success in this problem is defective. All right, pause it, and here are your answers. You should have gotten 0.131 and 0.0131, 0.9787, and 0.0213. This is exactly 10 right here. So that would be an equal to, so that would be a PDF function. And you have, make sure you put that in as 0.06. There is your n value, and that would be r. Less than 10 is less than 10. So in your calculator, you would have to realize that you don't care about the 10th one. You start at the 9th and go, and so this would be a CDF, and you would have to use 9. And at least 10 is greater than or equal to 10. And again, that's 1 minus what we just calculated here. So it should be, this should equal 1 minus 0.9787. And if you think about it, if only 6% are defective, the probability that less than 10 of them is pretty likely, because out of 80 products, less than 10 of them, yeah, that's what should happen, because there's not a very high defective rate, luckily. All right, that's it. I already spent way too much time talking today. Again, I just, this probability stuff is pretty amazing. All right, have a good day.